Yes, sir, please.
Just be back.
Okay, sir.
So current participants are from Adi Shankar College, or the externals one also have joined?
No, external, sir. We have
Okay.
90 or
No,
110.
so those who are
members.
joined currently, they are also external participants.
Yes, we have some external faculty
Okay.
members also joined.
Okay, so people are joining already. Okay,
Yes,
good.
sir.
Yeah. So yeah, good evening to everyone, and welcome to this. Program.
So let us wait for some more minutes
Sure, sure.
for all the participants to join. So we are sending the reminders in the WhatsApp group.
Okay. So just wanted to confirm, is my slides visible?
Yes, sir. It's visible.
Okay, okay.
Sir, sorry. Let us wait for 3 more minutes. We shall start
Okay.
by 6:05. Is that fine, sir?
Yeah, no issues.
Okay.
So
Okay.
I joined from another device just in case of any network issues.
Okay. Okay. Sir.
Ma'am, shall we start, ma'am?
Yes. Let us
Okay.
check Sarah's ready now.
Yes, ma'am.
Yeah, I am ready. So no
Okay,
issues.
sir. Then we shall start.
Okay.
Good evening, everyone. We now begin the first technical session of the fourth day of the 6-day ATAL-sponsored online faculty development program on advancements in cloud and edge computing, research and industry perspectives. Organized by the Department of Computer Science and Engineering, Adi Shankara Institute of Engineering and Technology. The first session of the day focuses on an emerging and impactful topic, edge computing, which plays a crucial role in enabling low latency, real time data processing and intelligent decision making closer to data sources. It is my privilege to introduce our first resource person for the day, Dr. Rajesh Kedia, Assistant Professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Hyderabad. Sir brings with him strong academic and research expertise in distributed systems and next generation computing paradigms. His session will provide valuable theoretical insights and practical perspectives on edge computing for research and real world applications. Sir, we are honored to have you with us today. I kindly invite you to take over the session and share your expertise on edge computing. Thank you, and over to you, sir.
Thank you very much, Parvati, and I'm also thankful to Dr. Ramani and the entire team of Adi Shankar Institute for coordinating this FTP and for inviting me to be a speaker in this one. So thank you very much, and I'm also happy to welcome all the participants who are doing this FTP for this session. So as I understand, today we have two sessions, one on edge computing and the other one following this on the fog computing. Okay. So let's okay, so this will be the outline of my today's talk. So what we will do is we'll quickly go through what is edge computing, where we need it and why we need it. And then I'll give you about perspective of what are the challenges with edge computing. Specifically, I will look into some details of how AI/ML workloads can be executed on edge computing and what could be some of the changes, some of the advances that would be helping that. Then I will give a brief idea of what are recent advances in edge computing, and then towards the end, we'll keep a small discussion where you can share your questions or any other opinions, and we could discuss about this. And in between as well, I will pause at certain points. So in case there is any question, you did not wait till the end. We could interact as and when necessary. So let's look at how computing evolved over the last 4 to 5 decades. So what we used to have at some point in time was mainframes where computing was centralized. People used to go work on those systems, and that's used to be the era of mainframes. But after that, we entered into the era of personal computers where everyone used to have their own computer at their home. Right, so this it was a desktop system earlier, and then gradually we had laptops. But this is all what gets classified as personal computers, where everyone had their own computers. We used to do computing, and there was a very limited requirement of having connectivity. A lot of things used to be at the individual's end. And then internet came, and then we connected all these computers, but still computing remained confined to local computers for a long time. Even though internet was popular, a lot of computing used to happen on local systems. And then in the last 1 decade or a little bit more, what we have is the cloud computing, where we can offload a lot of computations to cloud service providers through easy access because of a lot of advances in networking as well as other advances. Cloud computing started catching up. Right? So one of the biggest advantage it provided was you don't need to invest in any of the infrastructure at your end. Even if you have simple devices, you can do much larger scale computing through cloud. And then what we have as the topic of this FDP, as well as what we'll be talking today, is that now we also want what is called as edge computing. So cloud is there, cloud is evolving and helping, but it's not sufficient alone. We also need edge computing, right? And what is this? We will talk about in the next slides. So again, what we have is we have evolved from a personal computing, we went to the cloud computing, but then we identified that it has certain limitations, and then we come up with what we call as edge computing. And we would like to see what it is and what are the benefits and challenges that it comes with. So what is edge computing? Right? So again, the name itself. So what is edge computing is that rather than sending your computation to cloud, right? So when you ask any computation to be done on the cloud, you also need to share data. And we don't want to share data for various reasons. So what we want to do is we would like to bring the processing closer to wherever the data is generated, right? So we don't want to use cloud. We don't want to send our data to the cloud, but we would like to do the processing at the place where the data is generated. Or to give more details, it could be processing the data either on the same device where the data is generated. Now, how is data generated? Data could be generated through various sensors that we have, right? So we have camera, we have uh, location sensor, we have many other kind of sensors that we have. So data gets generated on these sensors, on these devices. And rather than sending this data to cloud for doing the processing, we are saying that we would do the computation or processing on the same device where it is generated. Or maybe if my device is not capable of handling such computations, I can process them on a nearby local server, right? Again, when I say local server, there is something which is accessible only to us, or maybe only to a limited trusted set of people. And it is not something that is a cloud being offered through a unknown service provider. Or it could be something which is a nearby edge gateway. So whatever it is, in summary, what we are saying is we need to bring data processing closer to the device, where or closer to where it is generated, and it could be processed either on the same device or on a local server or nearby edge gateway. We'll see some examples of these. Or in a way, we can say edge computing means processing without sending to the cloud. So when we say without sending to cloud, it means we are processing in the premises where the data itself is generated. Right. So that is how we can define edge computing. We can say what edge computing is. Right. Now coming to the next part of it, which is why we need edge computing. Why would we need edge computing? Maybe I can also ask some participants to just type. Are they allowed to type?
Yes, sir.
Yeah, so maybe you can just share some points. Why do you think we would require edge computing? So we have a good number of participants, I see 40 plus. Maybe anyone would like to share. Why would you need edge computing? If cloud is available, why not send it to the cloud? Why would you like to do any processing local?
Sir, it can be of two reasons. One is of security,
Okay.
sending a data to cloud, and other can be like for certain scenarios we need quick responses rather than to avoid the latency.
Yes. So there are multiple reasons. So I think the two most important reasons you have summarized. So one thing is that a lot of data could be sensitive data or private data which you don't want to send to the cloud. And the reason we are concerned about is we don't know where the cloud is, who is owning the cloud, and how the data gets used. Right. So that's one thing. So privacy is one of the important reasons why we would like to do processing in the edge, because if it is my data, I don't want it to go out anywhere. And then the second thing why one would like to do processing on the edge or near the data where it is generated is if you access cloud, it is through internet, it is through some network, and it is not always reliable. It is not always guaranteed to be available. What if you have more delay in the network? What if the cloud server itself is very slow due to a lot of load on that server? So there could be multiple reasons where you cannot guarantee that you will always get a response in limited time. And certain applications would require that you get the result, get the processing done in a given time constraint, right? So there could be this also is another important reason. So why would we would need time? So we can call them as privacy is one of the reason, as I said, and latency is another reason why you would like to do computing on the edge rather than going on the cloud, right? Uh, so these two being important reasons, there are certain other aspects that are there. So reliability, right? So as we said, what if there is no network at certain place? So you are having some device which you are taking in different places. For whatever reason, if there is a network outage or you are in a location where the network is not available, then do you just not do the computing or do you want to have something which can work, right? So that's something again where you would expect that reliability is available to you. Now, what could be those systems where you would expect better reliability? We'll see in subsequent slides. Scalability is another very important aspect why edge computing could be useful, right? So what do we mean by scalability is, let's say you have built a system today, you have something that works well for 100 users, right? And tomorrow you want 1 million users, you want to scale it to 1 million users. And if you have designed the system to just be working on cloud, and if you are not able to scale the services to that quantity, then you will find that while it was working well for 100 users, it's not working for the large number of users, right? But if you have edge computing where every user has a device in their near local premises and they are able to do the computing, then even if your number of users increase, as long as each of them have their device, the system is scalable, right? So that way, scalability is another added advantage that is provided by edge computing, which is not provided natively in a cloud-based system or any other similar system, right? Now, there is another aspect that we look at, which is cost. Now, cost, I put a question mark because cost slightly depends upon the cost of the device as well as the cost of the cloud services. Now, with edge computing, one advantage is once you have paid for the device, once you have bought the device, then you may not need to pay any recurring cost, right? Whereas with cloud, if you have some subscription model or if you have to pay per usage charges, then the charges may be higher. So again, cost is we cannot say that it is better in edge or it is better in cloud because it depends on how many such computations you are doing, how frequently you need to go to the cloud, and what is the device cost versus what is the cost. But cost is also something that can be one of the factor to be considered when we are saying why one would need an edge computing, right? So these are different reasons why we would like to go for edge computing. Now, what are the kind of applications where you think edge computing matters? Does edge computing matters when you have to do weather prediction? No, right? Because those are not the things where you are concerned about privacy or you would like to do them without going to the cloud. And so there are certain applications where you don't need to worry about the factors that we mentioned. So in those cases, we cannot or we would generally not like to go for edge computing, right? So for example, doing some scientific computations, let's say you are running MATLAB simulations, you are running any others evaluation tools simulation. Those places you won't go for edge computing. Now, where are requirements? What are the applications? What are the scenarios where one would like to use edge computing? So one of the very important place which is being talked a lot about in today's world is healthcare, right? And when we say healthcare, it is both health monitoring as well as treatment. So depending upon the medical conditions, sometimes doctors put wearable sense. Sorry, is there a question? Okay, so sometimes the doctors put some sensors, some kind of devices on patients so that you can keep on continuous monitoring of the health. And in case there is any anomaly detected, then you can maybe alert the doctor or you can alert any uh, relatives or any caretaker of the patient, right? So that's one place where a lot of data is continuously being gathered by the system and analyzed. Now, there are two options. One is you can send the data to cloud and analyze, but then as we said, it is not always reliable, and also medical data is very private, very sensitive data. We don't want it to be sent to the cloud. Right. So what we would like to do is we have some device nearby, either the same device that is the patient is wearing, or maybe the uh, some other gateway at the home where we could do this computation without sending the data to the cloud, right? That's one part of it, whether health monitoring or diagnostics, where we could use edge computing in healthcare. Also, nowadays, there are a lot of treatments that are happening through electronics, and for example, there's robotic surgery. There are some other things that are happening where you would require a lot of computation and you don't want to depend upon any external cloud or anything, right? So you would like to have the entire system ready and available to you in your own premises. So even for those kind of situations, we would like to use edge computing, right? So edge computing is important in healthcare, and more and more with more and more advances in healthcare technologies, the dependence of people on electronic devices is increasing, and that's becoming more and more important. The next place where edge computing could be useful is autonomous systems, which could be vehicles or drones or any other equivalent systems. And what could happen is, let's say you have an autonomous car and which is moving from one place to another, and it needs to what is it that it needs to do? It needs to continuously keep on sensing what is there around the.
Hello.
Hello.
I think there is an interruption at resource. Let me
I'll
check with him.
Okay, ma'am.
I don't know.
Okay. So in those cases, so what happens is a lot of computation goes on in the system. And again, if you put all those computations to cloud, and let's say the vehicle is moving in a region where there is no connectivity, then suddenly your system will stop working, right? So you cannot rely on those kind of systems if it is entirely dependent upon the cloud. So you should have a capability to moving from one region to other, it should be able to do the processing on its own, right? So otherwise, what will happen is you are sending a drone from, or even if you are flying a drone due to some internet issues, it will stop working. So we don't want these autonomous systems to be affected by network-related disturbances, and that's where there is a need to have local processing capability into these systems. Industrial setup, a lot of with advances in automation, lot of things in industrial premises have been moved to electronic based control. And for example, manufacturing houses, a lot of things are taken care automatically by electronics, right? Or even surveillance, where you want to see whether something going wrong or there is some kind of an action, some kind of an activity which requires immediate attention. So in those cases, again, you cannot rely on an external cloud. Maybe you also don't want to reveal those data to the external cloud. So again, all the concerns that we talked of, privacy as well as latency of action, this applies to here as well. And we would like to have a system which can do processing in the premises without sending it to the outside. Right? Now, one difference that comes between autonomous systems that we are talking of versus the industrial setup is that autonomous systems are moving from one place to other. Right. So here you cannot even rely on having, let's say, in the industrial setup, you can say that I will have one local computer system or a small server or something which can actually do the computation. Right. So you can say that my device or my computation system at least involves some local PC. But in case of vehicles and drones, you cannot afford them because these are moving systems. So whatever you have, you should have within the device or within the vehicle itself, right? So that's another difference that comes when we are talking of different kind of edge computing scenarios. So autonomous systems, because they are mobile and moving from one place to another, whatever edge computing facility we are looking at, it should be available within the system itself. Then we have a lot of things, different initiatives at the government level and at the even at the local body level, where we are talking of making a lot of cities as smart cities, where the traffic is managed in a smart manner, the emergency is handled in a manner where it is automated or involves a lot of electronic and digital decision making. So there also again we cannot afford to have things which are left to some unreliable situations due to networks or due to unavailability of the cloud, right? So let's say you have built up a traffic management system which relies on the cloud, and for whatever reason there is a cloud outage, right? So the service provider, whoever it is, there is an outage at their end, and even if that outage is for 10 minutes, it can lead to a big chaos in the whole city, right? Or if there is an emergency that you want to attend, but due to the outage at the cloud level, you are not able to attend to it, or you delayed the emergency by even 15 minutes, it can turn fatal for someone. Okay? So in all those situations, again, we would require to have some kind of a processing in the local premises, which can be something which is under our own control and is not affected by external factors. Right? Then there are many examples I can go up. I just picked up some few examples. So there is also a lot of AR VR systems now used for education, used for many other purpose, entertainment purpose, etc. Now in these AR VR systems, the whole purpose or the whole baseline is that we get a feeling of reality because of the speed at which they operate, the frame rates that they support. Now just imagine that due to network delays, you are going through an AR/VR system which lags and which is the frames are moving slowly. In those cases, what will happen is you will not get the actual intended feeling that you are supposed to get from such system, right? So these also, because these are generally this cost a lot, so you would not like to spend money and then leave things to chance or leave things to network situations. So you again would like to have a local or an edge computing setup in these kind of situations, right? So again, just to summarize, so what we have is we have edge computing requirements in many applications like healthcare, autonomous systems, industrial setup, smart cities, AI/VR systems, and many more. But it doesn't mean that edge computing is needed everywhere. So as we said, in scientific computing, in weather prediction, in DNA simulations, in a lot of this medical development where you are discovering new drugs and all. So all those kind of places can applications can still work on the conventional cloud or data centers or large supercomputers, but a lot of applications where human being is involved directly and where we need an action in a given time is where we would like to have edge computing supported. Now, coming to what kind of devices we could have which are considered for edge computing. Would we consider a big supercomputer for edge computing? No, right? Because neither we would be able to afford it in our local homes, nor it would be something that can scale to a larger number of devices, right? So what are the various edge computing devices that we have? So there are a lot of these small IoT devices, for example, the sensors that you have, something that is sensing the temperature of the room, something that is sensing how many people are there, maybe the cameras which are there. All these wearable, which I mentioned, are mounted on patient's body to monitor different behavior or monitor different parameters of the health. So all of these could themselves be edge computing devices. So they can have small microcontroller kind of a CPU which can do a little bit of a computing. There could be small memory, there could be some small support that they could have. So these could be some devices which could do some first level of computing. right? They may or may not always be able to do very complex processing, but some initial level of processing can be done on these devices. And if the overall processing requirement is simple, then these devices could themselves be the edge computing devices. If not these, then we can also have some smartphone where all of these devices connect to, and then they can use these smartphones to do the computing. Right? So as we know, today we have smartphones where we have multi-core processor. We have slightly better processors than what we have available in these sensors, cameras, and wearables. So one could use with all of these sensors, cameras can connect to smartphones. Now, this connection is much more reliable because this is a connection within the same premises. You can use, you need not use internet, Wi-Fi. Maybe you can use some technologies which are more reliable, right? And you can have smartphone or tablets or any other equivalent kind of devices which are more powerful than these IoT devices, and they can support processing the data received from different sensors. The other kind of devices which can also help do the computing is a lot of we have routers in our homes or in the premises, and we may have other network devices. So all of these devices also have some processor and some processing capability. So if we don't want to use smartphones, all of these small IoT devices can connect to each other through these routers, and they can use these routers computing capability to do the processing. So this is also one more place where you could do edge computing. Or as I said earlier, you could have some simple PC in your premise, some small, again, you don't say that we have a very high-end data center, but we can have a simple PC, or if it is vehicles already have a lot of processors inside them to do a lot of electronic system handling. So we can use those processors, or in the drones, we could have some processors. So all of these can also be used to do edge computing. And again, these are some examples. Based on some application, you can have one or more combinations of this, or just one of these being used to do edge computing, right? Now, what are the limitations of such devices, right? So one of the biggest limitation or difference from the cloud systems is these edge devices use simple processors, right? Unlike cloud systems, which might use the latest and the most advanced processors, these edge devices use simple processors, simple CPUs, which are generally embedded CPUs, and they follow what is called as RISC instructions, reduced instruction set computer. Again, we'll not go into details, but these are simple instructions, and they can the reason why we have these constructions is because they are simpler to implement, simpler to design, and consume less power. Right? Compared to the high performance CPUs, so in the cloud we will have CPUs like Intel CPUs, or in the server grade very high end CPUs from Intel or AMD or from any other equivalent companies. Whereas when we talk of embedded CPUs, we could have simple ARM. One of the popular companies ARM. We also have what is called as a RISC-V, and maybe many other embedded systems, CPUs could be there. Right? So they are limited in their compute capability, but they consume much less power, or they come at a much lower cost than the cloud grade CPUs. Also, when we compare the number of cores that we have, so on a embedded on a edge device, we will also one core, or maybe a single small number of core, right? So generally you will have many of the devices will have only one core, but you can have otherwise two or four or up to eight cores, right? You won't find a edge device where you have 32 cores or you have 64 cores. But when you talk about cloud and all, you can have any number of cores much larger than what you have in these edge devices, right? So one of the biggest comparison or limitation of edge devices compared to cloud is that they use simple processor, and when we say simple processor, they take more time to do the same job compared to what the cloud would take. And also they are limited in terms of the frequency that they support. So the cloud processors can support much larger frequency in terms of gigahertz compared to what the edge devices can support. When it comes to memory, or what we also call as RAM, the edge devices are heavily limited. Some of them, like the sensors and all, might have kilobytes or megabytes of memory. Whereas when we talk about the smartphones or routers, they may have a 2 GB or 4 GB or 8 GB of memory. You won't find edge devices which are 64 GB memory or something like that. But again, when it comes to clouds or servers, you'll find much larger amount of memory that is available. Right? So when you have larger memory, how does it affect computation? The If you have larger memory, you can actually handle much larger amount of data. You can do much more complex processing than what you can do in these edge devices. On similar lines, the amount of available storage is also less on edge devices. So how is this memory and storage different? So memory refers to RAM, whereas storage refers to your hard disk, or storage is refers to your flash or NVM, which is a non-volatile version where the data is not lost, right? So storage, for example, on your mobile phone, it would be generally like we would have 256 GB of storage. But on the small IoT sensors and all, you may have storage which is just a few megabytes or so. Right? Whereas when we compare the same thing to cloud, you will talk of TBs of storage, which is much larger than what you can have in the edge devices. Another biggest difference that comes is in terms of limited power or energy budget. Many of these IoT devices are powered by battery, and in that sense, they have very limited power. So they cannot keep on doing a lot of computations if it consumes a lot of power or energy. Right? So in that way also they are limited. So overall, there are multiple limitations, multiple reasons why edge devices cannot do all the processing that the cloud can do. And hence, there is a need to handle things differently for edge devices compared to just offloading things on the cloud. Right? But there is a need to do computation on the edge, and hence we must do something to enable processing on the edge. So with that, what we have done until now is we have discussed about what is edge computing, where edge computing can be used, and why do we need edge computing. And also we have discussed certain challenges with edge computing, essentially in terms of the devices which are available to perform edge computing. Right? So with that, I'd like to take a small pause and open up for any questions that we have from the audience. So rather than delaying the questions till the end. So any questions from the audience or anything that was not clear, you would like to repeat the same? Okay, so if there are no questions, I'll move ahead. And yeah, if you want, you can also type your questions, and once in a while when we look at, we will be responding to them. So don't refrain from asking any questions, okay? Okay, so now the next topic that I will be covering is related to edge computing for AI ML workloads. Okay. Now, first of all, why do we need to do AI ML workloads on edge devices? Why not put them all on cloud? Because AI ML, the lot of applications which involve AI ML take inputs like images or healthcare data or location data of the user, which a lot of them are private, right? So, for example, if I'm taking a photo using my camera, you see that there are boxes drawn around faces and all, right? Now, when I'm taking these pictures, I don't want to keep on sending this to cloud because this may involve a lot of privacy. Everyone may not be comfortable sharing their images to the cloud. So what we would like to do is this kind of this box that is drawn around each of the face, or sometimes it is able to identify this screen where we are taking the picture, etc. These are done through ML techniques, but we would not like it to happen on the cloud, but rather on our own device. Right? So even images have a lot of personal and private. So we may take pictures from our house, and maybe someone is concerned about any kind of uh, if we share our images, maybe there could be some theft or something else, right? So there could be a lot of reasons why one may not want to reveal their images. So we would like to process them on the edge. And same is true for healthcare. We mentioned earlier as well. So a lot of health data is very personal to people, and you don't want to send that to the cloud services. So you would like to process them local. And again, a lot of this processing involves AI/ML based processing. Similarly, for location and many other applications where you see AI/ML being used, but it involves private data. So that's the reason why we would like to do AI/ML on edge devices. Now, what is the challenge in doing it? For those who are aware of AI/ML techniques, they involve a lot of computations. Right? So don't worry if you don't know, but we'll not go into the details of AI/ML. But in general, these AI/ML applications, they involve a lot of computations, right? And also they use a lot of data. So, for example, if you have to process images, if you are taking a photo or video and you want to process it through any of these techniques, it's a huge data with a lot of high resolution that we have. The amount of processing and the amount of data that we have to deal with is very high. Plus, there are real-time requirements, right? So we have a hard time limit. For example, as we said, in a healthcare, if there is any anomaly that is there, we cannot wait for the internet to be available and then process it. We may want to process it as within a given time frame. For example, anything that happens within 10 millisecond or within 1 second, we should be able to inform the doctor, right? So we may have some constraints like this. Or if I am taking a photo or video, I should be able to. So typically the videos work at 30 frames per second or 60 frames per second, right? So which means that if I have 30 frames per second, I have only 33.3 milliseconds of time available to me to do the processing. And in many cases, it may happen that network delay is much larger. So in those cases as well, we would like to avoid depending on the external network or external cloud and do the processing uh, in a controlled setup which is available to me as an edge devices. Right? So these are reasons why we would like to, even if we look at other applications, for example, you have a vehicle that is moving and it is sensing the environment through cameras and making a decision on whether to apply brakes or not, right? So based on some of these ML algorithms. Now, we don't want to depend upon an uncertain situation and be not able to apply the brakes or take an action within the given time, right? So those are again some systems where we would have a very strong real-time requirements. And to meet these real-time requirements, we have to have something which is reliable even if we don't have a connectivity to the internet, right? So these are some reasons why I would like to have AI/ML on the edge. And one very good thing about AI/ML workloads, and that is something that has been exploited a lot by developers, designers, is that many of these AI/ML applications don't need 100% accuracy, right? For example, if I am doing a mathematical operation, I will always say that 5 plus 2, it should always give me 7, right? It cannot give me 6 sometimes, 8 sometimes. That's not acceptable. So that is the general computing requires a computation to be accurate. But when it comes to a lot of these AI/ML based applications, for example, if I have a picture and if I have 5 people in it, it is okay to have only 4 of them being identified. People don't mind so much if the fifth person who is little bit away from the picture not able to identify, right? So a lot of ML applications are inherently resilient to inaccuracy. Even if you do computations in an not accurate manner, these applications are able to do their job to some extent, right? So that's something which is there, which is what we call as an approximate computing, or introducing approximation. And we'll see how some of these things have actually helped us improve the AI/ML execution of the edge devices. Right? So we'll see some examples of algorithmic advances, approximation, and hardware advances that has helped us achieve a efficient AI/ML execution on edge. Right? So by default, you may say that it works fine. You can run something on the device, but if it doesn't meet your time requirements, if it takes 5 seconds to just find to do some processing on a given image, then you will not be able to meet the real-time requirements like 33 milliseconds. Or in a case of a vehicle, you may have to take an action in within maybe 10 millisecond or even smaller unit of time, right? So what we want is we should be able to do processing efficiently in the given time on these edge devices. Coming to algorithmic advances, so there are many different ways to do AI and machine learning based processing. And things have evolved a lot in the past few years. In the earlier times, we used to have, for example, if you have to detect, given an image, if you have to detect a face inside it, there used to be some techniques based on image processing, right? So basically, you go through each of these one by one and find out certain aspects or certain features, and then there's a lot of algorithmic way of processing it, right? So you do this like that. So those techniques used to be there, but they were not very accurate. They used to take a lot of time and were not very efficient to implement for edge. And then we came up with what is been used a lot in such image processing and image-based ML is what is called as CNNs, or convolutional neural networks, right? So what convolutional neural networks did is they converted this whole algorithm into some kind of a data-based processing. So you have all the image pixels being given to you as different inputs. You do some processing just to find out certain characteristics and generate some more values, or some what we call as features. Then you pass it on through different layers, and at the end, gradually what you do is you identify whether there is a face in this, whether there's an animal in this. So there are different kind of processing you can do to get different information about the given image, right? And it need not be image, it could be any other signal, any other kind of data as well, and you can identify certain useful features from that using CNNs, right? Now, what happened is there were a lot of CNNs that got developed, right? So some of these are for specific tasks, some of these can support many different tasks, right? Now, as an edge developer or as a system developer for the edge device, you can choose the one which meets your requirements, right? You need not always go for something that works. Something that works for one person may not work for another system that is being there. So based on what you have, there are many choices that are available in terms of which kind of algorithm or which kind of neural networks or what is the model that you want to use for AI or ML. Right? So they have been evolving, and with time, there have been models which are smaller and are able to give similar amount of accuracy as compared to older model. So there have been regular algorithmic advances. People have been trying to compress the model, reduce the model to smaller size, and without compromising on the overall accuracy or the performance of the model that we can achieve. And also there are many different variety of models. Some are very small models which can do some task uh, quickly, but at an approximate level. There are large models which can actually do things in much more precise manner, but they take more time, right? So now depending upon the system that one is developing, so if you want to run, for example, you want to run something on a sensing IoT device, right? Let's say you want to do something near the camera itself, then you can use a smaller model. But if you want to run the same thing on a mobile phone or any other better device, you can use a larger model. So depending upon where you want to run the algorithm, what is it that we want to achieve from the application, we can have different size of models, different kind of models that are there. And it is an interesting exercise to identify the right ML model to be used. Right? You cannot just pick up something that is existing and saying that because someone else used it, I will also use it. No, it depends upon what is your application. So healthcare may require a different ML model versus a different application might require a different ML model. Right? So that's also something that because we have different advances in algorithms, so we have come up with very different kind of models, which makes the choice large, but we can have things which are suited for particular kind of application. So similarly, we have other advances in various ML models. We have how so while CNNs are good at handling static data, there are time series networks which can, if you have something that is happening over time, right? For example, speech or something where you cannot just say based on something that is there at one time, but overall across time, what is the words that you have spoken, all those things where you have these devices which can detect your command and take action based on what you are saying. So all of these are different networks that you may want to use. And then recently with advances in generative AI and all, so there are transformer models that are also there, which we could run on these edge devices. Again, that depends on where we would like to use it. But there are different models that can help achieve some of the AI ML applications on edge devices. Now, coming to the kind of approximations that one could do. So, why we do approximations? As I said, these AI ML models, they are not very specific about having exact computations, right? So, they are okay to have some approximation, some inaccuracy in the processing if it saves the either it saves time or it reduces the requirement of memory or CPU to perform the computation. Right? So there are two popular kind of approximation techniques that exist in when we execute these AI ML workloads. So one of them is called pruning. Right? So what is pruning? So just to give you an example, so let's say I have a CNN model where I have a lot of inputs that are coming and I'm generating many other inputs which are going to the next layer. This is what we call as layers. So layer 1, layer 2, layer 3, like that we have different layers in a CNN. Right? So output of one layer goes as input to the next layer. Now what pruning says is that can we reduce some of these data? So can I eliminate some of these? Can I reduce a few of them? And is that okay? Is that acceptable for overall computing? Right? So that is what we call as pruning. We reduce the total number of parameters or total number of computation points that we have. Right? So if you look at it in details from another perspective, so CNNs can be modeled as some kind of matrices. Right? So again, how does that happen is not the focus of this course, but what internally the processing requires is you convert this CNN in some kind of matrix operations, right? So and you have one matrix and another matrix, and you do matrix multiplication, right? So that is the standard operation that is involved in a CNN. Now, if I can reduce the size of these matrix elements, let's say if it is n cross m matrix, if I can make it as n minus something, n minus p cross m minus q. If I can reduce the number of elements that are there in the matrix, it will automatically reduce the complexity of computations, right? So my number of computations will come down. So what will it do is it will reduce the number of metric multiplications that are involved. it will also reduce the storage or the memory requirements, right? Why? Because now I have less number of matrix elements to consider. So it also reduces the memory requirement. So it doesn't just reduce the number of computations, it also reduces the memory and storage, right? So that way, this is one very popular technique, pruning, used to reduce the number of parameters in the model. Now, what will happen if you reduce the number of parameters? You may be able to, you will see that the accuracy is dropping. Right? So as we said, if you do less, if you consider less parameters, you will see that the accuracy is dropping. But people have come up with very efficient way to find out which parameters to prune, and the accuracy drop, they are keeping it much less, something around less than 0.5% or maybe very small number, right? So that has been a lot of research in how can we do efficient pruning for these AI/ML workloads. And why we do pruning? We do pruning because by doing pruning, we can fit them on these edge devices, right? Otherwise, they would exceed the available memory. They would not be able to compute in the given time. But if I prune them, I reduce the overall complexity of the model. I can actually run them much faster, and I can fit them on the available memories of the edge devices, right? So there are different works on pruning. One of the very popular approach, which actually is a very unique kind of pruning, was mobile net, where people said that earlier we were not able to execute neural networks on mobile phones, and by doing such kind of structured pruning, we were able to reduce the we were able to fit the mobile CNNs on mobile phones. Right? So that's one thing. There are many other works on pruning. Now, what can you prune? You can prune the number of parameters at each level. And sometimes people say we can also prune the layer. Why to have multiple layers? Can we reduce the number of layers? That is also a possibility that is there. And that way, there are many different things that one could prune, or basically, it's cutting down on the computation. The other way to simplify or reduce the overall computational load and make such AI/ML workload execute on these smaller devices is what is called as quantization, right? What does quantization mean? Quantization means that you reduce the width of each parameter, right? So in pruning, we are saying we will reduce the number of parameters. But now in quantization, we are saying let the number of parameters be the same, but can I reduce the complexity of each parameter? Right. So for example, if I have each parameter in the original design as 32-bit parameter, can I reduce them to 8-bit parameter? Or can I reduce them to 16-bit parameter? Right? So how will this help? Any thoughts? How will reducing 32-bit to 8-bit or 16-bit help? I will still have that many number of parameters. I will still have to do that many number of computations. But what is the benefit of reducing the width of the parameter? So
Time saving.
sorry?
Time saving. I quick
No, but
process it.
why
That's the
will it
number
save
of
time?
bits are
So the
reduced.
question is, why will it save time? Instead of 32-bit, if I use 8-bit, why will it save time?
See, everybody needs a quick response, right? That's why.
Yeah. So basically when we reduce 32-bit to 8-bit, what we can do is we can use simpler hardware. We don't need a complex hardware. We can have small adders, small multipliers, which can handle 8-bit. Or if I have, instead of 32-bit, if I have 8-bit data, so we have something called as vector processing in our CPUs, where you can process multiple things in parallel. Right? Now, if I have 32-bit parameters, I can process only limited number of things in parallel. But if I have 8 bits, I can have many more number of parallel processing that is possible. Right? So that is one benefit that you get by reducing from 32-bit to 16-bit or 8-bit. The computation hardware becomes much simpler. You can do more amount of parallel processing if the hardware allows it. The other benefit you get by reducing from 32-bit to 8-bit is your memory requirements come down. Even though we are not reducing the number of parameters, but because we are reducing so a 32-bit parameter will require 4 bytes of memory, whereas a 8-bit parameter will require only 1 byte of memory, right? So if you have 1000 parameters, in the earlier case, you'll spend 4000 bytes. Now you'll spend only 1000 bytes, right? So that way also your number of memory requirements also comes down. And as we have seen, memory is also limited in these edge devices. So by doing quantization, you can take care of memory issues as well as computation related issues. Right? So quantization is another technique. And both pruning and quantization are independent of each other. You can apply only pruning, you can apply only quantization, or you can apply both pruning and quantization. Right? So what you say is, I will reduce the number of width and as well as I will reduce the total number of parameters. So in that case also you can save and get benefits of both of these techniques. Right. So there are many more approximation techniques that are there. So this is a broad classification of what we call as approximation, or sometimes these are also called compression techniques. So what we are doing is we are compressing the model. We are reducing the overall size that the model will otherwise require. And by doing such kind of compression, we save on memory space. We also reduce the overall computation complexity that we have. Now coming to hardware support for AI/ML models, so there are many different kind of things. So it's not just that people have evolved people have improved only the algorithm, or they are trying to compress the models. But also from the other side, we are saying, can we have hardware support? Can we have hardware-based techniques which can help us execute AI/ML models better on edge devices? Right. So one of the very big contribution from hardware for this is developing accelerators. Right. So what is an accelerator? Accelerator is a very specific hardware device which can execute or which can perform only the given kind of computation, right? So it's a very dedicated and a custom device for a given application. So what we do is we design accelerator for, let's say, for CNN, right? So we have an accelerator for CNN, which can execute CNN much faster and better than a general CPU, but it can do only CNN. It cannot do anything else, right? You cannot ask it to do anything else. But because people found that lot of edge devices require execution of AI/ML models, they integrated CNN related accelerator into these hardware, right? So that's one very big inclusion in the edge device hardware is we have now many edge devices have CNN accelerators into them. And similarly, we also have embedded GPUs. So as you would have already known that GPUs are very popular in ML execution. They are able to do a lot of things much efficiently for machine learning. But edge devices used to lack GPU, but with recent times, we have been able to have smaller, simpler GPUs which are available to these edge devices, which can be used to offload some of the ML computation to the edge devices. Right. So what we get by this is we get something which is not as complex as a cloud-based GPU, but something which can do things much better than using the simple CPUs that we have on these edge devices. Right. And we have also been trying to increase memory. So as you know, with technology improvements that is happening, memory size is increasing and the cost is coming down. So because of that, people have been adding more and more memory. Again, you can see as an example, the phones 2 years back used to have memory around 2 or 4 GB, but today they are having 8 or 12 GB of RAM available to them. Right, so that way we have been increasing memory, we have been increasing storage on the hardware devices that we have to execute the edge available at the edge, and with that we are able to support more complex execution. There's also been a lot of work on co-design of hardware and software. Right? So what does co-design means? You don't just design hardware alone and software separately. Can we design them together? Can we have hardware and software being designed together so that it is overall better? Right? And this is itself an interesting research problem. This is not a new problem. This is an old problem, but just that now we are talking of co-designing hardware and software for AI/ML. In the older time, people said co-designing hardware and software for image processing or for signal processing, speech processing. So application has been changing, but co-design is as such a problem that is there from old times, right? So what we are saying is, if I am building an accelerator, and let's say I come up with the best accelerator, but if my software is not able to use this, then what's the benefit I am going to get? Right? And vice versa, if I am having a software which is much efficient, but if I don't have a equivalent hardware, then what's the use of it? Now, if I can design them together, what will happen is I can make certain compromises in hardware, I can make certain compromises in software and come up with a very nice solution that works together for both. Right? So that's another thing that has been happening. So with that, a lot of hardware vendors are providing their own software libraries which work much better on their hardware, and then we can use them to support various AI models. So these are things in terms of including hardware or doing the hardware design. There is also an equivalent and important aspect of, now we are talking of all these edge devices, many of them don't have just one core, but they have multiple cores, right? Now, when you have multiple cores, which task runs on which core is an important decision. You cannot keep on running everything on the same core, and you cannot keep just use the existing technology to use any one core to do whatever, right? So each core has certain differences. So now can we have better task mapping, and can we do something which is aware of these models, which can actually help improve the overall time, overall power, and many other things, right? So this is something which is generally handled by a power task manager or the task to core mapper, which is available in the OS in general, or we can have our own custom drivers which can handle this. And then coming to a better use of the hardware knowledge. So let's say if I know that my system CPU has a given amount of cache, let's say if I know that it has 1 MB of cache, then can I use it in a better way? Can I change something in my overall model which works better, right? For example, if I know that I have a 1 MB of cache, then can I choose, instead of choosing a so we said that we have models which could be small or large. So can I choose some model which fits better in 1 MB or which works better for 1 MB than something which is much larger, or something that is much smaller, which is wasting my size, right? So if I have some knowledge of what I have in my hardware, I can make better decisions. And similarly, compiler can do a better job when it is generating the code. So if it has to run this matrix multiplication loop, it can partition it in a way that this we call this as a tiling. So it can partition the whole matrix into small sized tiles such that the tile that fits 1 MB better can be actually used. Right? So these are things that can be done along with the compilers. Or if we know that our hardware has some vector instructions or any specific instruction which can be more efficient than the standard code, the code compiler can generate those codes being aware of hardware knowledge and then use them better. Right? So these are again some of the things that goes along when you have to do better or efficient execution on the edge. If you just care about running something, that's a different thing. But if you want that things should run efficiently, then there are different things from hardware or from hardware plus compiler or from operating systems that could come in. based on the knowledge of the hardware, they can do some better decision making. Right? So with that, what we have seen is we have seen how we can run ML models better on edge devices. So we have different models. We can choose the right one as per our requirements. That's first thing. The other thing is we can introduce approximation or compression techniques, which can reduce the overall computation as well as reduce the memory requirements. Two very famous approaches towards that is what we call as pruning and quantization. And then we can also have a lot of hardware support, hardware-based techniques where we can have custom hardware for doing this processing, or we could have better memory, or we could have co-design of hardware and software, or we could use OS and compilers help to perform better ML model execution. So with that, what we have done until now, we have covered what is edge computing. We have seen what are the challenges with edge computing. And then we have seen some examples of how we can do edge computing for AI/ML on limited devices. Again, when I say edge computing for AI/ML, there are a lot of research that is happening where people are saying that can we run AI/ML on small devices as small as having 256 kilobytes of memory, right? Just imagine 256 kilobytes, nothing very small. Even one small photo that I have, it will be 5 MB, right? So they are very small devices, but can I run even simple edge in AI/ML models? Can I just say whether there is a person present or not present? Can I just use it to do very simple checks and very simple automatic inferences? And people are saying, can I run AI/ML models on mobile devices? And mobile devices vary across range. So some very low-end mobiles have 2 GB or even smaller memory, whereas a high-end mobile can have 16 GB of memory, and even number of cores would be different in these devices. So when we say, can we run it on mobile devices, this itself is very large range because different devices can have different amount of resources available to them. And this is a broader picture where we have AI/ML requirements on every small device as well as we can have AI/ML being run on edge devices or gateway devices or network devices as well, right? So we can run AI/ML models on various kind of edge devices. Let's look at some of the new things that are there in the hardware or in other aspects which are helping in the overall edge computing. So there is something called heterogeneous cores that is there. So by default, when I say I have a multi-core system, let's say I have a processor with 4 cores, by default, it means that all these 4 are similar kind of cores, right? But with recent times, what we have is we are starting to have a heterogeneous cores. So if I have 4 cores, 2 of them could be big cores, 2 of them could be small cores, right? How does this help? If I need a large compute capability, I will use the big cores. But in case I don't need it, I can use the small cores only so that I can save on energy and power, right? I can shut down these big cores and you just use the little cores to do simple tasks, and that will save my energy and power, right? So energy is important. You don't want to keep on charging your mobile every time you do some computation or anything else. You don't want to consume unnecessarily a large amount of battery. So it is important to have such kind of a heterogeneous or mixed system. Whenever you need large, you use it, but if you don't need it, just shut it off and use smaller ones, right? So this is something that has happened. And a lot of edge devices are now, earlier, which used to be limited either on because they were consuming a lot of power or because they were not able to do a lot of processing faster due to limited CPU capabilities, can now you are giving them best of the both, right? So they can do something. And having said that, this is available in ARM and all the recent desktop systems and all that we have. There also we have. So instead of big and little, what we call them as performance cores. Anyone has heard of these terms?
Yes, sir.
Yeah. So nowadays, all these Intel, AMD, and all these CPUs, they have earlier they used to have 8 cores and all. Now you see they will have 20 cores. Right? Why 20 cores? Because out of this 20, only 4 are big cores. Rest all small cores. So we are able to afford a lot of small cores in the same cost that we would have otherwise just have at big cores, right? So all these heterogeneous systems are becoming more and more popular. Even the M1 chip or M2 chip from Apple, that also has something like this. They will have 4 performance cores, 4 efficient cores, right? So this is something that is happening and is available in all different edge devices as well. And then, as we said, we are adding more and more accelerators which are for specific custom requirements. So we have neural processing unit which can do CNN execution. We have image processing based accelerator, something which can process image very efficiently. Rather than doing it in a CPU in a general manner, we have a dedicated accelerators, or you can call them as specialists, right? So just like you have specialists who can do the same task much better than a general purpose person. Similarly, accelerators can do the same things in much better way. So we now, you will see that various devices have accelerators which can do CNN, which can do image, which can do video, because these are the requirements where you have a lot of computation, but you don't have enough processing power, right? So and a lot of people are using these applications, so it makes sense to have dedicated accelerators to handle these kind of requirements. And as I said earlier, also memory capacity and speed both have been evolving and improving with time. There has been a lot of so one reason why we go for edge computing is we say that there is uh, issues in terms of dependability on the internet and all. So there are standards, there are 5G and other things which are improving connectivity, at least within the devices, you can have connectivity across the devices. So there are a lot of improvements coming in connectivity due to newer standards. And that also enables us to have dynamic edge versus cloud computing. Right? So we said that edge is needed. So if privacy is not a concern, let's say only latency is the concern, and somehow you know that the network is much better in a particular place. Let's say I'm in my home and I have a very good internet. So why not use cloud in those cases? So there is also option to have dynamic edge versus cloud. So you monitor the network speed, and based on that, you decide whether you want to send something to cloud or you want to do local computation on the edge. There is distributed edge computing, where instead of having computing happening on one device, you have multiple devices at your home and you use all of them to do the computing. There's also something called fog computing, which is in between edge and cloud. You have some better trusted cloud, but that is not the actual cloud, which is the remote cloud, right? So you have something in your own premises, which is slightly better than the edge devices, but are trusted and connected with reliable network to the edge devices. And also something that has been helping a lot of edge computing is there has been a lot of improvement in battery and power management techniques that is helping us reduce the power consumption of processing on the edge. So that is also something that helps the edge computing, right? So some of these advances that has helped the edge computing. And one of the biggest advantage of edge computing is you can have many, many devices which are doing edge computing, which are doing the computation without affecting each other. So what you do in your premise has no connection to what I am doing in my premise. So we are not affecting each other, and we can easily scale if we have these many number of devices with us. Right? So these are some examples of advances in edge computing, or advances in processing, in networks, in other things which are helping to better edge computing. And with that, we would like to quickly summarize the topic. So we have seen that edge computing involves computing things locally without going to cloud, and primary reasons for them are privacy, reliability, scalability, and latency. And these devices are typically limited in the available resources, which could be due to CPU limitation, memory limitation, battery limitation. And common edge devices are the mobile phone, the sensors, the network gateways, or some local processor or local PCs that we could have. Specifically for AI/ML, we have seen that there are a lot of algorithm or at approximation or hardware-based advances that could help us perform AI/ML based computation, but on local edge setup. And AI/ML, because it is becoming more and more popular, a lot of people want to use it, but it has a lot of computations and also some real-time requirements. So that's one of the focus area for today's world on edge computing. Having said that, it is not that we should only study or we should only consider AI/ML workloads. There are many other things which we could which could be used to, which could be deployed on edge. And we have just taken AI/ML as an example. And there are other things that we just discussed. We are having better edge devices. We are also talking of things about edge plus cloud dynamic switching and many other different kind of things which could actually. So the whole objective is to ensure privacy, to ensure the required latency is being met with a better with a better overall experience of using in the system, right? So it could be due to only edge, it could be due to edge plus cloud, it could be due to whatever are the other options that the developer has. So with that, I complete my this lecture on edge computing. The primary aim that I kept was I'll try to motivate and give you a perspective of what is edge computing, what are the things that are there in edge computing and all, so that you are aware of the terms, you are aware of some of these concepts, and it can help you explore more and more things on your own from the web. And also it will provide you a baseline so that you can understand the remaining part of the FDP better. So with that, I end my lecture. Any questions, I would be happy to take. I just project this screen as a small recap. So if there is any question, please let me know. You can type or you can speak up as well.
Dear participants, if you have any questions, you can use this time to pose it to sir, please.
Sir, in between, I had another question.
Yeah.
But the edge and cloud dynamic switching answered it. And I wish you to explore or say, give some light on tiny ML. How?
Okay. Yeah. Yeah, thanks, Dr. Mani. I wanted to speak about it. I spoke, but I didn't use this term, so that's a very good question. So tiny ML. So what is happening is, as we said, ML is becoming popular. A lot of people want to execute ML, and we want to execute ML on. So everyone knows that we can run them on cloud and high-end data centers. But what if we want to run them on very small devices, right? And what tiny could mean is, as I just mentioned, so tiny could mean that we are running it on a small device, which is a 256 KB device or something that might be in a small toy that a kid has or anything else, right? So tiny ML involves running ML in very tiny devices, right? And these devices are having very less amount of memory in terms of RAM as well as storage, right? So how do we actually run these ML models on such tiny devices. So one of the very important thing that we do is we do a lot of compression. We compress the model significantly, and we compromise on accuracy. Definitely, we don't say that we do it on a full accuracy level, but we compress the model a lot. We also consider this TinyML for situations where the images that we want to process or the inputs that we want to process could be of smaller resolution. Right? It's not a very high-end 1000 by 1000 resolution image, but it could be even as small as 28 by 28 or some 56 by 56 resolution image. Right? So there could be very small images. So this is one thing that we do. We compress the input, we compress the overall model to be processed. What we also do for such kind of TinyML execution is we'll do a lot of optimizations on memory access pattern, and also something that I mentioned, if I have small memory, I would like to use it much more efficiently. So there are a lot of techniques that we deploy there to reduce this. So what I can suggest is there is a work, there's a lot of work from MIT on this direction, where they have a demo and they have the entire code on GitHub where they're running this small CNN models. So you can just search for MIT and TinyML. You will find a lot of resources. There are a lot of interesting research works on running ML models, CNNs, and even recently, I think, transformers on such very small devices. So that's there. So the main idea is bringing ML on tiny or smaller devices, and that is something which is TinyML is. So there's a lot of effort from various groups. One of the very recent and popular is this from MIT. You can check that.
Hello.
Yes.
Good evening, sir. This is here this side Bhavesh Kumar Sharma, Shada University, Greater Noida. Sir, I want to ask the questions. The actual difference in the real scenario, the difference between distributed computing versus fog computing, edge computing. What are the real differences, sir? Because, sir, I have used applications in the AWS. So I
Yeah,
am bit
see, edge computing, as I said, is computing at the edge, computing it within your local premises, right? Edge computing could be with only one computing device, or you could have more than one computing device. Distributed computing means you are doing computation with lot of different small, or maybe large number of servers, and you are distributing the task to them. So you have a large task, you distribute to different computers or different processing devices, and they together work to give you a result.
fog computing, sir.
Fog computing, as we said, comes in between cloud and edge. So in fog, what you could have is you could, let's say you have a better small, at your home, you have set up one server, and now you are asking the server to process something. Or let's say you are in an institute where you have a smaller uh, trusted cloud which you have. You are not going to AWS, or you are not going to any other external cloud, but you have a fog. I think fog you will get more clarity in the next lecture. So let me not take that surprise also from you. But when it comes so about distributed computing, it is involving more than one computing devices, which could be on the server, which could be on the cloud, wherever it could be. But it is more like it's not restricted to your local premises, whereas edge is restricted to the local premises.
Okay, thank you, sir. Thank you, sir.
Thank you.
Sir, good evening, sir.
Yes.
What are the major key performance metrics used in evaluate the edge computing in especially research, sir? Key performance metrics used
Yeah,
in
so
edge
one of the key performance of edge computing is that the latency, right? So firstly, you should be able to meet your latency requirements. That's one thing, right? If you are not able to meet, so privacy is guaranteed by default because you are not sending the data outside, but you should be able to meet your latency requirements. And then there are other things, for example, power consumption. Are you consuming more power or less power? So that depends on the research topic. So generally, hardware designers would look at power and latency as metric. Maybe some other overall application developers could look at cost also as a metric to be considered, or how frequently you have to, let's say, charge your device. That also could be considered as another metric. So there are many different metrics depending upon who is actually uh, looking at that metric.
Okay, thank you, sir.
Yeah, thank you.
So personally thank Dr. Meenakshi Madam no, for contacting you and facilitating this session possible with you, sir. Thank you so much. So before wind up, I'll have one quick question. Sir,
Yes,
agentic AI is now ruling the industry right now. Is there
yes, yes.
anything about no edge computing in that direction?
So I think here it's a very good point. So what can happen is, let's say, if I have a small agentic system, and if I deploy it on edge edge devices, and it can maybe decide that something that can be, so I mentioned this, we can use this edge plus cloud combination, right?
Yes,
So
sir.
agentic AI can actually help it much easily, because then we can decide, okay, something which can be done locally and something that requires a lot of computation, much more complex problem, we can give it to the cloud. So I think those
Yeah.
kind of things could be
Right.
integrated better.
Yes, sir.
That
Yes, sir.
that's
Thank you.
a good point.
Yes, sir.
Thanks.
Thank you. Thanks.
And yeah, so if there's no more question, then I would like to thank the whole organizing team and all the participants as well for staying back till the end of the class. Thank you very much, and best of luck for the next sessions.
Thank you very much, sir. The session was truly insightful and beneficial to all of us. Thank you very much.